That would be so sad. Alrighty. So here we go. We're gonna go a little bit into partial fractions and then we'll probably take a break around 11-ish, okay? So here we go with partial fraction decomposition. So I feel like the first time I heard when I was a student, I was gonna be learning something called partial fraction decomposition. It was like such a long name that I just felt intimidated. Also, the word fraction is in there. So if you don't have a really good friendship with fractions, then the idea of fractions inside of something else can be like even more not fun, okay? But I want us to kind of start with, you know, some things that we know about fractions and sort of laying them on to what's new. And then we'll actually do a problem about when are we going to see this again. So again, the big idea is that we want to really know when are we going to see things again. So I think that kind of helps us understand the importance of these small little pieces that we're learning. Sometimes if we're like, we're never going to see that again, then it's kind of like, well, why are we doing it, you know? But let's go back to what we know. So let me ask you this. 1/3 plus 1/2. Okay? 1/3 plus 1/2. Without a calculator, how do I solve this problem? Yeah, we want a common denominator. How is 12 as a common denominator? Is 12 a common denominator for 1/3 and 1/2? Yes. Okay, so 12 could work, right? What other common denominators could I use for 1/3 and 1/2? Okay, but so is 6. Yeah, and I really like how you said that, Isis. You're like, well, yeah, 12 is, but so is 6. And I think the importance of that is in this case, 6 is the better option. Okay, why is 6 a better choice than 12? Yeah, it's not just the common denominator, it's the lowest common denominator, right? And so smaller numbers are easier to deal with. Exactly. These are all super good points. So let's not do what I suggested. Let's not find 12, even though it's valid. Let's find a common denominator of 6. So the way I like to set these up is I sort of leave a little bit of room in front of the first fraction and a little bit of room in back of the second fraction. And I think about what I need to multiply each one by to get a common denominator. So what do I need to multiply the first fraction by to get a denominator of 6? Okay, 1/2. Or 2/2. Which one is it? Is it 1/2 or is it 2/2?
Well, if we multiply by 2/2, then it's like the same as multiplying by 1.
Okay. So 1/2. What I like about the 1/2 is that we knew the bottom had to be 2. Okay. And one of our sort of magical tricks in math is if we multiply something by 1, no matter how we say 1, but if we multiply it by 1, we don't change anything. And that's the important thing. We don't want to go changing the question because then we're going to change the answer. Okay? So for the first fraction, our fancy way of saying 1 is 2/2. What is our fancy way of saying 1 for the second fraction? Like, what do I have to multiply 1/2 by to get the lowest common denominator of 6. Good. 3 over 3 is our fancy way of saying 1. Okay. So now, let's see, we get, how do I multiply fractions, by the way? How do I simplify this? Okay, we got one thought for cross multiply like that. What do other people think? Straight across? Okay. So let's kind of go up here and sort of clarify a situation. So if I have a fraction equals another fraction, okay? I have a fraction equals another fraction, then I want to cross multiply. But if there's no equal signs between my fractions, if I have this, a over b times c over b, then I just multiply across, so a times c over b times d. Yeah, and don't worry about it. I'm actually really glad that you brought that up because that's the #1 mistake. Folks are like, I don't know, people tell me about cross multiplication, so I'm just gonna do it because I think that's what I do when I see 2 fractions. But we want to modify that statement for ourselves and say we multiply straight across when we are multiplying fractions. So we'll get 2 over 6 for the first fraction, and then the second fraction becomes 3 over 6, and now we know we have 5 over what? 5 over 6. Good, because we add across for the top, but our whole deal with finding a common denominator is we only have to add the tops. Okay? So that's what we know. And in this simple example, we've talked about a few ideas. The lowest common denominator, okay? Not just any common denominator, but the lowest one, okay? We've talked about fancy ways of writing 1. And I'll highlight that 1 in yellow so we know. Sorry, is the sound getting weird for you? Just did an update on my computer last night. I'm not sure if that's adding to it. Sorry, that's probably no fun on your ears. Sounds windy. Windier than normal. Okay. Well, we'll go with it. Hopefully, maybe after the break, it'll be a little bit better. Super valid. No more mosquitoes. No mosquitoes. All right, so we've talked about the lowest common denominator. We've talked about fancy ways of writing 1. We talked about cross multiplying versus multiplying across, okay? And now what's new is we're gonna take these skills that we know how to do with numbers and we're gonna throw some variables in there, okay? So what's new? We are gonna be, whoops. Applying these concepts to fractions with variables. Okay? So we're going to apply these concepts to fractions with variables because that's how you know that you're doing some grown-up math when there's like less numbers than you've ever seen before in your life. okay? I turned in homework for one of the classes that I'm taking, and it was like 4 pages of essays. I was like, I don't think I even have any numbers in here. It was just like all these words. So there's different levels to like how we do things, but what we're doing here is trying to generalize what we know about fractions with numbers and applying those to fractions with variables. Yes, exactly, Christina. So we're going to try and multiply by 1, but we're trying to find that lowest common denominator, okay? And the way that we write 1 is going to be different depending on the problem. All right, so when will I see this again? You will see this again for those of you who are going to Math 150. Okay. So not Calc 1, but Calc 2. Right? So I'm going to show you a problem, okay, but kind of like the difference quotient one where I showed you this fancy problem in the beginning and then was like, but let's just look at a small part of that. We're going to do that same thing right now. So I'm going to show you where you're going to see this again in this big fancy problem, but then we'll focus on a smaller part of this problem so we kind of understand what it is that we're learning and how we might apply it again in the future. Okay? So when we get to Calc 2, we're going to see something like this. Right? This little symbol in the front is an integral symbol. And if you have an integral, you 100% need a dx at the end, okay? And then we're gonna figure out how to integrate this particular function. And so if I'm integrating, what I need to do is figure out, is there factors for the bottom? So x squared minus x minus 6, yeah, I could factor that into x minus 3 times x plus 2 dx. So already I'm seeing that even in a higher level math class, that idea of factoring is so, so important. Because if I don't know how to factor, I can't do this first. And then I'm going to say, well, gosh, I don't know how to integrate this, but I could integrate it if it looked like this. A over x minus 3 plus b over x plus 2. And so then this is the part that we're going to focus on, which is how do we take 3x plus 11 over x minus 3 times x plus 2 and break it down into its partial fractions. A over x minus 3 plus b over x plus 2. Okay, so this step right here, like the word that follows this, is what we're going to focus on in our class. So as you can see, I actually should probably move this over a little bit because what I'm trying to do is think about my question, the 1/3 plus 1/2. And I want to think about what fancy ways I can write 1 so that I make the 2 denominators match. Okay? We'll see where those went in a little bit. So what is the common or the lowest common denominator for x minus 3 and x plus 2? Yeah, each other. So if I multiply the first one by x plus 2, then I've made this partial fraction have the same denominator as the other side. Okay? But if I have x plus 2 on the bottom, what needs to go on the top of that fraction? The x plus 2. So this right here is our fancy way of saying 1 for this particular scenario. How do I say 1 for the second fraction? Perfect. X minus 3 over x minus 3. Good. And this is our fancy way of saying 1 for the second fraction. Okay? So really what I have is a times x plus 2 over x plus 2 times x minus 3 plus u times x minus 3 over x plus 2 times x minus 3. I wonder, by the way, if the wind that you're hearing is right now my computer sounds like it's going to take off and fly away. So I think that might be part of it. Okay. So I multiplied my fancy way of saying 1. Now, let's kind of go back to this idea of the 1/3 and the 1. If I think about this 5 in the numerator, so 5/6 equals 1/3 plus 1/2. Yeah, that's probably it. I know, my poor computer, I turn it off. I turn it off every night, but sometimes I think it's really stressed out that it has to work all the time. Okay, so this 5 in the numerator is kind of like our 3x plus 11. But if you look in the original fractions, like where it came from, there's like a 1 on the top and a 1 on the top over here. So in our original question, there was no 5. That was like after we combined our like terms and found our lowest common denominator, that's where the 5 came from. So David, to kind of answer your question about what happened to the 3x plus 11, the 3x plus 11 came from some number times x plus 2 plus some number times x minus 3. So let me ask you folks sort of a separate question. If I have 3/7 and I tell you that's equal to x over 7, what does x equal? 3. 3. Perfect. How'd you know that? How did you guys get that so quickly? Because, like, don't you have to cross multiply and then figure out what x is? You guys did that really fast. Yeah, they're the same. There's an equal sign, both numbers have the same denominator. If it was a different numerator, it wouldn't equal exactly. Okay, what about this? 3 over 7 equals x plus 1 over 7. What does x equal now? Very nice. Okay, so if the denominators are the same, do we really have to worry about them when we're solving for them? That's a good question for us to think about. If the denominators are the same, do we really need to worry about them? And the answer is no. Okay? So if the denominators are the same, what we can really say is we can kind of cross them out and say x equals 3. Or in our second example, we can say we don't need to cross multiply and then distribute and all that stuff. We can say cross out those denominators that are the same, and now we have 3 equals x plus 1, and everyone can solve that. We know x equals 2. That same idea applies to this giant fraction that we've now created. This denominator is the same as this one, which is the same as this one. Once we've made the denominators the same, we have the freedom to get rid of it. And all we're left with is a smaller equation that just deals with the numerator. 3x plus 11 equals a times x plus 2 plus b times x minus 4. So once I have the denominators the same, I can cross them out and just set up an equation with the numerator. Okay. Now our job is to find a number for A and a number for B. So let's go. 3x plus 11 equals ax plus 2a plus bx minus 3b. Now, we just spent the last week talking about systems of equations. And we started off with systems of equations that were all linear. So a throwback to our middle school and early high school days. And then we graduated to systems of nonlinear equations, where we looked at all of the conic sections that we learned about and how they look when they cross with a line or with each other. This is another extension of systems of equations. Let's check this out. I'm going to collect all the terms that have a 3x equals ax plus bx. What's the greatest common factor for this equation, 3x equals ax plus bx? It's the x. So like I've done with the other greatest common factor, I can divide that away. So really I have 3 equals a plus b. Okay. Now let's collect all the terms that don't have it. Plus 11 equals 2a minus 3b. That'll be our second equation. 11 equals 2a minus 3. How can I solve for a and b here? Sorry. How could I solve for a and b here? Elimination or substitution. Cool. All right, if we're going to use elimination, let's go ahead and multiply the top one by 3. Yeah, then I can get rid of the b. So 9 equals 3a plus 3b. 11 equals 2a minus 3b. 20 equals 5n. A equals 4. I have my A value. How to find my B value? Plug it back into one of the equations. Doesn't matter where, but let's pick the easiest one. B equals 4 plus B, B equals negative. All right, so what does that mean? That means way back up here, everywhere I see an A, I can put 4. It also means that everywhere I see a B, I can put a negative. So this question that I started out with, this one right here, instead of saying the integral of 3x plus 11 over x minus 3 times x plus 2, I can write it like this. The integral of 4 over x minus 3 plus negative 1 over x plus 2. Let me write that down. Now, one of the things that you may choose to do is say, I know plus a negative means just subtraction, so you might want to write it like this. Integral of 4 over x minus 3 minus 1 over x plus 2, and that would be okay. So I'm going to pause here for a moment and say that this part right there in the green squiggly, that's what our focus is. That's what we're going to work on today. Okay, this thing inside the green bubble is called partial fraction decomposition. The stuff I'm doing after this green bubble is Calc 2. You don't need to worry about it, but I just kind of want to show you where we're headed with this. And that this stage right here is so important to getting to be able to do all the other questions that we're going to see in Calc 2. Okay. So let's say we've done this, we're at this stage, then at this point, you can do a few things. You can pull out the constant, and people like to do that. And people like to split the integral into 2 integrals. Up to you. Or natural log, we've learned about those before. So this part here that we've done so far outside of the green bubble is the calculus part. And as you can see, it's so much shorter than the algebra. This is the thing that makes calculus hard for students and why as STEM core we said, let's get algebra first. Let's make sure that our students have a solid foundation in algebra so when they get to calculus, this is the part that they can focus on. Just the slightly new part of information. But even this answer right here, depending on who you take Calc 2 with, they might want you to simplify this more. Okay? So what we can do here is we can actually go back and use what we know about log properties. Okay, log properties, that's going to be on the final because we're going to see that stuff again. Okay? So in case it's a little bit back there in the brain, let's kind of talk through this about what we can do. But with the properties, I can take this constant, I can bump it up as a power. So natural log of x 4 minus natural log of x plus 2. And how do we combine when we have two natural logs separated by a subtraction? Anybody remember how we combine those? Yeah, exactly. That minus is like the division. So you might even see in some textbooks they write their final answer there. This plus C. Okay. So this is an example of when we're going to see this particular topic again, okay? Nested inside of a bigger topic. Okay? Now again, as you're studying, I don't want you to freak out about all these other weird symbols and letters and things like that. I want us to focus on the things inside that green bubble. So if you've taken calculus before, you'll know that when you integrate and there are no bounds, you need a plus C at the end. Okay? If you do have bounds, finding a specific number, then there's no plus C. But this is called a general solution. And it just means that we have a variety of values of C that could make it work for this particular question. Okay. And if you go up to differential equations, you'll spend a lot of time solving for C, like what is the number for C? How can we generalize it for a variety of different real-world applications? All right, so I know I probably don't have satisfactory answers for some of these really great questions that are coming through. It's not that I don't think they're worthwhile. I think we are definitely going to be answering those questions when we get to them in the future. But for right now, I just wanted us to think more like, how are we going to use this again? When is it going to come up? Okay. So I think this is actually a good time for a break. Maybe I'll actually even power down my computer so that I can hopefully get this fan sound to stop. But let's go ahead and stop sharing.